If you haven't had a good read of this question, then I suggest you pause the video and read through very carefully yourself, underline important pieces of information, and of course that always involves numbers, and as well as, in this case, obviously talking about bearing and your understanding of how to translate that to your diagram. So, yeah, like I said, if you could even attempt to do draw the diagram before you actually see mine, that would be a good idea, and just simply pause now. So you can see there that I've put in my compass points, north, south, east and west. It says leaving from a town, both cars leaving from town. Always put where they're leaving from in the middle. And you can see I've written town there. Car A travels on a bearing of 125. 125 is obviously between 90 and 180. So it's in this quadrant. And for 48 kilometres. I'll just fix that up, put a kilometres on there. And car B travelling on a bearing of 215, obviously between 180 and 270. 215 comes between there. And that's car B, and I should have 60 kilometres here. Now, I've put all the information on there. There's nothing very obvious at the moment about a right-angled triangle. So that's the next piece of work that we have to do, is establish where this right-angled triangle is. So I'm going to redraw. Car B is sitting down here, and there's 60, and car A is sitting out here at 48. Probably you could see ideally we might want a right-angled triangle in here, but we can't just assume that. What we do know is that right around to B was 215 degrees. If we work out the difference between that and 125, then you can see now that yes, that difference is 90, which sits in here. Will you be told to do this? The answer to that is no. They're the things that you have to be able to work on within the diagram. So now we have our right-angled triangle. And you will perfect that, because you know that bearings come within trigonometry. Trigonometry requires a right-angled triangle. So, we're actually asked to calculate the distance between the two cars. So we could call the distance between A and B in this right-angled triangle x. So in this case, actually, we don't need trigonometry. The reason we don't is because it's a nice right-angled triangle. We know two sides. This side is the hypotenuse. We could simply use Pythagoras' theorem. Now, this is not something that I had previously revised. But should that ever be the case, and the reason that it came to mind was because there was no angle given. Neither this angle or this angle were given. So I'm thinking within my right angle triangle, I've got two sides being asked to find the third side. That is Pythagoras. That is using c squared is a squared plus b squared. I guess the more familiar you are with these concepts, the more likely you are to make the connections to them as well. So my x squared becomes 48 squared plus 60 squared. X will be the square root of that, 48 squared plus 60 squared. And that becomes 77 kilometres to the nearest kilometre. Now in C we're going to find an angle bearing of car A from car B. That's really important where the bearing is given from. At the from position, we draw our north-south. Oops, I thought we were going red. North, south, east, west. North, south, east, west. The bearing from B to A is actually this angle. Now, this is not an easy question. Not easy at all. You can see now I've redrawn the diagram. So back to the original, town was here, car A went off there, car B came down here. At the moment, the question is asking us to find all of that. That's two angles. That's this angle on the outside and then theta on the inside of our right angle triangle. We could find theta without too much trouble within the right angle triangle because we know this side is 48 and this side is 60 of our right angle triangle. So with respect to theta, this is opposite and this is adjacent because A to B is the hypotenuse. So we could use tan to find theta. But theta alone is not the answer to the bearing. The bearing is the angle from due north around. So due north of B around to A includes these two separate angles. I'm just going to dot this angle. So the bearing is the red dot plus theta. Now, like I said, theta we can get from our trigonometry, and you'll see me do that in a moment. The way that we get the dot is to use our parallel line properties. So I'm just going to draw this, realizing that these two now are parallel. So we're going to have two parallel north lines cut by this transversal. We've got a red dot in there, which is what we want, but what we know, it is the same as the red dot in there because alternate angles are equal, which means we need that little bit of the angle, that little bit of the 90 degrees. If we think about where that came from, we know that down here to B was originally on 125. It's like going back to this diagram and finding just that little bit. How much past 180 is 215? So in fact the red dot is actually equal to 215 past 180. How much is that? That in itself is just 35. 20 there to 200 and another 15 is 35. So I've got the red dot is 35, and I got that not doing any trigonometry, actually doing geometry, parallel line properties. To find theta, we'd established that in that right angle triangle, to find theta we need tan. Tan is opposite on adjacent. Opposite side is 48, adjacent is 60. To find the angle we take, tan inverse. Tan inverse 48 is, as you can see there, 38.65, etc. So we'll say 39. Therefore, the bearing would be these two added together. So we had 35 and 39, which is 74 degrees. And I guess, strictly speaking, we turn it into a 3-digit number. So there's lots in that example, and I doubt that you would comprehend and get it all in one go. I'd strongly suggest you revisit this video several times, jotting down any questions you might have. And seeking clarification of that. This is definitely a harder question, but many of you are more than capable of accessing the marks that will be allocated to these more difficult questions. So please keep at it. You've done really well so far, so just keep at it and you will master this.